This set of notes covers both concave and convex mirrors, which are two different types of curved mirrors. Concave refers to mirrors that curve inward, while convex, kind of like the back side of a spoon, curves outward. So the first type of mirror that we're going to look at is a concave mirror. Sometimes it's referred to as a converging mirror because it will take parallel light rays and bring them together. So here's an inward curving, concave mirror. If a light beam were to come in horizontally and strike the top of the mirror, it will bend downward, and you can kind of go through that again just like your flat mirror. If I were to add the normal line at this location, I'll draw it in blue. All right, notice the normal line, which makes a 90-degree angle. All right, basically bisects the incoming light ray and the reflected ray. If I were to continue moving through this, all right, I have to move that again. If I had a light ray come off the bottom, all right, it would bounce upward. And I'm gonna get rid of this normal line now just so that you can focus in on what's going here. If I had a light ray strike the middle of this mirror, that's where it's essentially flat. So if I had a light ray come straight across, it'd bounce straight back. And as you've seen, where all these light rays come together is referred to as the focal point of that mirror. If I were to measure the distance from this location right here back to the mirror, this is what's referred to as its focal length. If I went through the same process with a convex mirror, it's referred to as a diverging mirror because it will spread the light out. So if I had my three oncoming or incoming light rays hitting the top of the mirror, bounce up and away, at the middle, straight back, towards the bottom of it would be downward, and notice that all three of these reflected light rays are spreading out. If you were to, like a flat mirror, backtrace all three of these reflected light rays, you will find the focal point. And a focal point for a convex mirror winds up being behind it. Let's move ahead. All right, so for a particular concave mirror ray diagram, if we had an object that happened to be located outside the focal point, you can draw what are called principal light rays. These are a couple special light rays that can be used to locate the image. All right, light comes off of this object in many different directions, so we're just going to choose a couple special ones. First one that we draw, if we send a horizontal light ray straight across, as we saw in the previous slide, it will bounce downward and through the focal point. Okay, that's one light ray. If I draw another light ray off the top of the object towards the mirror, if I send one through the focal point, notice that the normal line is kind of oriented this way. So when this goes through the focal point, it'll bounce off horizontally. A third light ray that you could draw is at the center of the mirror, and at the center of the mirror, the normal line goes along what this is called the principal axis. And notice this angle right in here, angle of incidence equals angle of reflection. And notice that all three light rays meet at this spot. So that's where our image appears. And notice all this light came from the top of the object. So this location here corresponds to the top of the image. And we wind up getting an image that is upside down. And this image is also real because these three light rays actually meet at this spot. Notice the image is in front of the mirror and not behind it. So I kind of jumped the gun here, right? So with a plane mirror or a flat mirror, you got a virtual image because you could not project it onto anything. The light was not actually at that location, okay? In this past slide, we actually had a real image, right? Because they actually meet at that location. If we go through another situation with a concave mirror, if we were to put an object directly at the focal point, this is a very special case. If I have a horizontal light ray, bounces through the focal point. I cannot draw a light ray through the focal point because I'm sitting on top of it, but I have that option to draw one at the center of the mirror. And look at this geometry here that appears. These two reflected light rays are perfectly parallel to each other. They're not going to meet over here, and even if you backtrace them onto the other side of the mirror, they will not meet there at all. In this case, you get absolutely no image whatsoever, okay? Because nothing, all right, will meet. Next case, you can move the object inside the focal point. And if you send a horizontal light ray, just like before, it will bounce through the focal point. Now you cannot draw a light ray through the focal point because that would be backwards, but you can draw a light ray towards the mirror as if it came from the focal point. So if you take your ruler, put it on the focal point, and line up your ruler with the top of the object, you'll get a light ray at this, at this orientation. Okay? And if it comes from the focal point, it will bounce off horizontally. Notice that these two light rays will never, ever, ever meet. But if you backtrace these two reflected light rays, they will meet behind the mirror at a higher location than the object itself. And you will get a magnified virtual image that appears to come from behind the mirror. Okay, so you get these three different cases with a concave mirror depending upon the location of the object. Okay. And this slide here is just meant to summarize these three different situations. All right, so we're outside the focal point, we get a real inverted image. The word inverted means upside down. At the focal point, no image at all. If we're inside the focal point, we get an upright, large image, virtual one behind the mirror. Okay. We'll talk about this later, but when we do the math, but the image distance here is negative. And I know you're getting that cut off of this video right now, but not a big deal. Okay. Large concave mirrors, we are going to use one. We're going to go outside, collect some sunlight, focus it at a point, and it will be enough to burn. All right, so some fun ahead. Okay. Concave mirrors are also used in telescopes to collect vast amounts of light, focus it, bounce it towards a flat mirror, plane mirror, back to your eyeballs, right, through the eyepiece. And this is how you can see, wide areas of images. Convex mirror ray diagram, a little bit different because your curve is outward as opposed to inward. Remember, the focal point then winds up being behind the mirror rather than in front of it. So if I were to put an object in front of it, here's our trusty arrow. The first light ray we will draw is horizontal once again, but it's going to bounce off of this mirror up and away as if it came from the focal point. If I send a light ray towards the focal point, right, it's not going to get there because the mirror is going to get in the way, but it will bounce off perfectly horizontally. Notice that these two reflected light rays will never ever meet, but if you backtrace them, notice the red one back through the focal point, the black one horizontally, they meet at this location, but notice that it gives us an image that is upright but smaller than the object we had. All right, if you ever look in a convex mirror, all the images appear small. All right, and this is the reason for that. Okay. So there's only one case with a convex mirror. You place it anywhere, you're always going to get a virtual, upright, small image that appears to come from behind the mirror. Okay. The image distance in this case, once we delve into the math, will also be negative since it's on the opposite side of the mirror. It also has a negative focal length because that focal point is behind the mirror. Convex mirrors, your security mirrors to pick up shoplifters, right? It's distorted, but everything looks small, but you're able to see a wide field of view because of the convex nature of the mirror. The math here, it's referred to as the thin lens mirror equation. Right now we're just using it for mirrors. It allows you to find the location of an object, an image, and its focal point. I sometimes refer to this as the if I do, I die formula. It helps students remember it, where the F is the focal length, D sub O is the object distance measured from the mirror, and DI is the distance of the image from the mirror. Up here, remember, these are the number 1, right? These are not I's. It's 1 over F, right? They're reciprocals of these. So one quick example of this, and you'll have plenty of practice doing this, is if we had a concave mirror with a focal length of 10 centimeters and you put an object 5 centimeters from the mirror, what image would you get? All right, so we can do the math on this, right? The focal length is 10. All right, it's positive because it's a concave mirror. The object distance is 5 centimeters in front of it. All right, we have a lowest common denominator of 10, do a little bit of algebra, and you will then have to flip this, and you see that your image distance is negative 10 centimeters, which tells you that you have a virtual image on the opposite side of the mirror that appears to be 10 centimeters behind it. Thank you for watching, and start your mirror problems.